what we just looked at is new geometry is put on to R3, right? R3 already has this geometry called the Euclidean geometry, right? Dot product and angle and all that, we know that. But we put a new geometry by using different matrix, right? And also different metric. It is induced by that. Geometry is a more richer structure than the metric. Metric is only about distance. Geometry have more length and area, volume, angles that has all that in that. And also, if it is something like this is a curly C, the continuous function defined on 0 to 1. If it is open up to a non-compact intervals, and the space gets really complicated, but defining inner product and all that is easier if you look at entire continuous function on the 0 to 1. This is a mere vector space. That's all we had before, right? There's no other geometry in there. But we put the geometry there, give birth to the geometry and the metric on this space. Set of all continuous function. Vector space, now it has the geometry and the metric. The metric, what was the metric? Remember about this one? If I have V and W, what are those V and W? Those are two functions in this space. What was the inner product? Integral from 0 to 1, the function V and function W multiplied if the main variable is X. This was it, right? So that's the space. Was vector space, now it became a geometry. And here, this time we're focusing on the metric. Metric is that if you have two vectors, what is the metric between that? Before it was called distance. With this metric space, it has this wonderful property called triangle inequality, right? Which is satisfied by all metric space. But this metric space induced by this inner product space has one more thing, special thing that all the other metric space does not have. Metric space is a more rudimentary structure than inner product space. It's a Pythagorean theorem. What was Pythagorean theorem? V plus W squared is V squared plus W squared, right? But what was the condition on V and W? It's not always true. If V and W are orthogonal to each other, then it becomes that. So here's V, kind of its intuitive picture. That's the W, right? In R3, if you're chasing around like this represents V plus W, right? So if they are, orthogonal to each other, and that's Pythagorean theorem. That's what we have. And also what we're entering here is infinite dimensional vector space we're entering. Okay? Infinite dimensional. And we're not going to look at too complicated infinite dimensional. We're going to only look at infinite dimensional vector space whose basis is enumerated with a number that we feel comfortable. 1, 2, 3, 4, 5. Right? This is called countable. You might have learned this cardinality, countable, uncountable thing in your proof course. Right? Countable means there is a set you can label these things using simple number 1, 2, 3, 4. But the real numbers, and there is a really interesting proof that there is no scheme of labeling 1, 2, 3 such that you cover all the real numbers. You always run into contradiction. So we're only considering vector spaces whose basis is countable. Or not too complicated, something that we understand, but it's infinite. Right? So here's an example of such things. Do you remember what this one is? Span of the PR, polynomials, right? So polynomials. What are the bases of a polynomials? Standard basis. Start with 1, second one, x and x squared. This time it does not end, right? Let's go forever like this. So does it look like a countable basis? This entire thing is labeled by 0, 1, 2, the number that we understand, right? Okay, so remember, but think about this in general V1 and here. So one thing is that if V has an infinite dimension, countable basis, we restrict ourselves to that. But and in here, one thing you have to notice is that this infinite sum is not inside this V. Whenever we enter this infinite basis, but this infinite sum is not the element in the V. We only allow the V finite sum of infinite choices. So let's say F2, F4, F6, up to F200. The sum has to be finite. That's what is inside this V. The fact that you have infinite bases does not allow you to take the infinite sum and put it in there. Let's go back to this polynomial. We understand a polynomial, right? This thing going forever is not a polynomial. Is not in the polynomial, right? Okay, polynomial must end some point, right? So it's natural that you don't confuse. You can get yourself, don't confuse about this one. But if you enter abstractly like this, sometimes you can confuse about. All right. In even an infinite dimensional vector space, this infinite sum is not allowed. But finite sum is allowed, and what's involved in it as a finite sum is infinite. Infinitely many choices involved in this finite sum. Could be 200 sum of 200 thing. It could be sum of 2,000 things, and something like that. Right? Does anybody know what this function becomes? 1 plus x and x squared plus x cubed forever? This was 1 over 1 minus x. This geometric series and stuff like that. Right? Is this really a continuous function in between 0 and 1? Because if you write it like this polynomial is not a function. But if you want to identify this one inside the continuous function 0 and 1, then we have inner product in there, right? Up to here, no need to introduce inner product when you enter this one. But when you put it into like this, usual purpose, and you enter the inner product. What is the inner product of this one? Integral between 0 and 1 of this one, right? But you can see at 1, it diverges. So this guy is not in here. Okay? But you can imagine, maybe we can find something in here. For example, if I switch this negative x and plus x squared, negative x cubed, you need this alternating thing, right? Alternating. And this one becomes 1 over 1 plus x. Okay? Is this inside the polynomial? No, right? But is this still inside 0, 1? It's true, right? It's still in there. So that element is still inside in here. It's a continuous function between 0 and 1. But it is not in the polynomial. You already know this phenomenon. Q is a metric space. It's not a vector space. I'm not looking at the vector space. I'm looking at its metric space, right? If I'm writing down 1 minus 1/2 and 1/3, 1/4, 1/5, if I stop here, this is an element in the Q, right? But if I go forever like this is not necessary in the Q. That's the phenomenon. We're looking at some metric space. It has a distance is defined. Then if you add it finitely many times, because of the vector space structure, you know it's in there. But whenever you add it infinitely many times, then you're not sure. Sometimes it's in there, sometimes not, right? So do you know what this number is? I think that was ln2, right? ln2. So Q is there. If you add it like this, becomes ln2 is outside this Q, right? But where is this thing inside? Real number, right? So something like that. We start with a polynomial, and then we begin to add things as many as you want. And then you end up with this infinite thing. We know it's not in there, but we know it is something bigger, right? Bigger world, a continuous function, not polynomial world. And this process is called completion. You're looking at a certain system of vectors. It has metric in it. If you happen to add infinitely many times, then this convergence is there. This is not going anywhere. If you're in the number line, these guys are all going here somewhere, but it is outside of our understanding, which is called rational numbers. And you have to go like this, right? And the same thing, we have a polynomial world. It has metric in it. And you will keep adding these vectors, and you realize it's not in there, but it is in the bigger world. And this would be kind of completion of all that thing. So there's a general procedure like this. If I have a vector space, it has infinite bases, like this, and then we can consider all the finite sum element is fine, but happen that to have this, we looked at this certain series that is going to infinite. We carefully examined that it's not going to infinity or anything. It is kind of trapped somewhere in between. So it seems like it's converging somewhere, but not in the world that we just constructed. It's not in V. It's not in polynomial. Somewhere else. Then you have to fatten this one, enlarge this world, V, to something bigger, right? That process is a Hilbert space. That's what a Hilbert space is in physics, in chemistry. You have understanding the vector space structure, and you got to throw in everything that we can kind of reach using this infinite sum. All right? So let's just get used to this idea of the infinite countable bases allowed. So another important example is that, and wondrous example, is this trigonometric polynomials. So it's a span of 1 cosine x sine x, cosine 2x sine 2x. You see the pattern? Cosine 3x and sine 3x go forever like that. So what are the elements in there? Finite sum of this collection with the coefficient r thrown in, right? If you throw an infinite sum, then you have to think about it a little bit. Is this a meaningful function? And then you have to enlarge it and things like that. So this is the infinite sum is coming out of this is called the Fourier series. All right? And because the shape, you can just change the coefficient to different shape, like cosine pi x and cosine 2 pi x, things like that. You can throw in this uniform factor. But if you make it simple as possible like this, cosine x and cosine, the usual inner product structure in here is going from 0 to 2 pi, or another interval of negative pi to pi. That is the, if you do this, this one behaves nicely. Easier calculation. If you multiply any distinct element in here, they're all 0. Right? You've seen that in the exercise problem. So if you write it like this inner product space, what is wonderful thing about this guy in here? What kind of basis is that? Quiz problem. Somebody got this one right before. It's not orthonormal. It's orthogonal basis. If you integrate this one to itself, the integral is not 1, but non-zero. So you have to normalize it with the root pi and things like that. But in practical purposes, that's not very important to me. So I'm keeping it this way, and it's orthogonal basis. Any two thing you choose, multiply it, integrate, becomes 0. With a polynomial, that was really nasty. And here, this natural thing already orthogonal. All right? So they use this a lot. Instead of, if it is between 0 and a to b, this is the better basis than polynomial basis. The polynomial basis is really nasty. That polynomial is called orthogonal polynomial. So if you go to Mathematica and type orthogonal polynomial, they have prepared it for you already. So you don't have to actually do the Gram-Schmidt process. They made it for you. So you can just use that. Things like that. All right. All right, focus here is a metric. And here is this important problem. Minimum metric problem. Okay? So here's an example. You might have seen this in the first year in algebra. This is plane sitting inside R3. Okay? And here is a 0. Therefore, is a subspace. If this plane does not go through 0, it's not subspace. It's called affine space. So it's kind of shift of that space. So there is a vector v out there. And we're looking for points on this H that's the closest to v. Closest to v. And everybody can locate that, right? Where is it? How do you describe that? I'm v here. Which point on this plane is the closest to v? So that is it. V minus u. U is here, running around this plane H. When is this one smallest possible? That's what I'm saying, right? The minimum of this one. And everybody knows that you go directly down here, and that's u0. That's the minimum value. Everywhere else, because of this triangle kind of thing, you see that is always greater than. All right? So we use this visualization, and we use this full Euclidean geometry. Only thing we're going to have is actually inner product, and we'll try to formulate this observation only in terms of inner product. So try it here with a dot product. All right. So this perpendicularity is important, right? This dotted line perpendicular to the entire plane. So how would you represent this dotted line? V minus u0, does that look like the vector? You've done that in Calc 3. The vector starting at the u0 and going to v is v minus u, that directional vector with a point of application at u0. In terms of dot product, what is the property? This one is perpendicular to entire vectors that is starting at the u and anywhere landing in this h, right? Starting in here, go anywhere. These vectors are perpendicular to this vector here, called the normal vector to the plane. So if you dot it with something, it's going to be 0, right? What is this something? U. And u is coming from where? H. Starting from 0 and an h. If there's a u0 such that v minus, this is fixed, right? Fixed vector. V minus u0 dotted with a u coming from everywhere is a 0. That must be this one. Correct? From this picture, I think it's intuitive. But what is not intuitive is that, all right, this one directly translates to v minus u0 with inner product, an abstract space, right? 0 for all the u that is coming from some subspace. Okay? You can't visualize this, right? But we want to kind of show that it's actually possible there is u0. And how many u0s are there in here? Only one u0 you observe it in here, right? In this abstract inner product setting, we want to show that there is u0 that inside this H that satisfies this property. And how many u0s are there? Only one u0s are there. We have to explain that, not relying on this, right? Once you have that, and this u0 is called, what is it called? It's orthogonal projection of V onto H. Okay, so here's a theorem. V or less than finite, doesn't matter. But to do this process, it seems like it's important. Let me use this word. It's convenient that we're just looking at finite dimensional subspace sitting inside infinite dimensional, such as polynomial infinite dimensional, H polynomial degree up to 6. That's finite dimensional, right? And V is anywhere in the infinite dimensional vector space. Then what is the conclusion that we wanted to draw in here? There is U0, right? There is U0 like that. So there is U0 where it's supposed to be projection onto H, right? It's going onto H such that what kind of properties are satisfied? V minus U0, that thing in here, is orthogonal to everything that is in H. We want that. Not only we just want to know it exists. How many? One and only one that it exists. That's the theorem. Okay? Here's an existence part. It's a theoretical existence, so using orthonormal basis and things like that is really convenient. First, the case is that if V happened to be already inside H, all right, then what do you think about this case if it's difficult to visualize it? And here, we chose this V already inside H here, not actually off the plane H. What is your candidate for U0? If it is outside, it's orthogonal projection, right? If it's already on H, what is your candidate for U0? All we have to show is that there is this vector such that everything else is that, right? Set U0 to be, if it's already in there, itself is one idea. The V is in there, and what is orthogonal projection is that V itself. And see if that's really satisfied. What is V minus U0? 0 vector, it's the same vector. So it's automatically 0 no matter what U is, right? So let's consider the case that V is not in H. I'm going to consider the W, that is a span of this V, and the sum is actually a direct sum of H in here because V is outside. So is that okay if I put direct sum in there? The direct sum is outside. Then prepare H as a span of E1 and E2 like that. What is this E1 and E2? Remember what this notation E stand for? Orthonormal basis, right? Orthonormal basis. How do you know that it exists like this? Gram-Schmidt process allows you to do that. All right? But what is the dimension of W? One more than H, so you can extend this one. Remember, there's a Gram-Schmidt process if you throw in one more, and you can just extend it like this. All right? Then this is a basis of the W. Anything in here is linear combination of this, and especially the V that we're interested in orthogonal projection is a linear combination of these things, right? Not V1, but E1, E2, all the ways to AL, EL, plus AL plus 1, EL plus 1. the exact shape of A1 is not important, it's existence. Does that make sense? The V was in here. We have a new basis. Therefore, there must be a linear combination of this one. And it turns out this is really the U0. So without explaining how we got this one, just have to verify that V minus U0 is EL plus 1, and that is orthogonal to everything. So here is a U, right? What is V minus U0? V minus U0 is AL plus 1 EL plus 1, right? But what is U? U is coming from H, right? All these H's are always looking like this. BK, EK, K going from 1 through L. You have to stop at L so that it covers exactly up to H, right? Any H element in H is represented like this. Okay? And this one is precisely BK, AL plus 1, EL plus 1 in a product with EK, where K is going from 1 through L. But what is this one here? L plus 1 and K never touches L plus 1 is all below, so they're always a 0, right? So it's a 0. No matter what U you choose, V minus L is EL plus 1 that is orthogonal to any basis in the H element, therefore it's guaranteed that. So that one is called the orthogonal projection of V onto H. So it exists, right? Still not clear if there's a one and only one, because it depends on your choices of Gram-Schmidt process. Somebody applied Gram-Schmidt process to different bases, then it's going to be different orthonormal bases, and from there I don't think it's clear that this is going to be the same thing. So it's really worth doing that uniqueness. This U0 is unique. There's no other vector that has a property. Okay? I'll stop here.